Hi, hello, welcome to section. So this isn't the typical like section content kind of things. Really, all we're doing today is going over the section mini exam, and then because the section mini exam's somewhat short, it's like not a full exam. I also want to go over one of the questions from the practice exams from you, specifically one question from practice exam 1B at the end. And then even with that, I think that we'll probably have some time for questions to like go over individual things. So that's kind of the game plan for today. I know that Chris said to come to section having done the mini exam. Can I get like a show in the chat for the folks who are here? How many of you have like done the mini exam? And then maybe also like how'd you feel about it? Of like good, fine, meh, not so good. Work. Okay. Okay, solid. Yeah. So we're going to go through the whole thing for the mini exam. And literally, I'm just going to talk through solving each one of these. And then I'll like pause for like questions for each one after we've kind of talked through some of it. Also, my full disclosure, I have glanced at this mini exam once, and so I'm not super familiar with it, but I think that we'll be able to figure it out. And then I also think that like seeing me thinking through it will be helpful for y'all to think through how to approach it too. So without further ado, let's go ahead and jump into the question 1 on the mini exam here. So, okay. First off, this I think is going to be roughly similar to page 1 of the exam. And honestly, I think that this page should be the kind of gimme points of the exam. These are going to be probably the easiest points to get. Now, don't feel bad if you still like miss questions on this, especially here as you're practicing and getting it together. But you are going to be asked to identify functional groups and then also identify hybridizations. It looks a little wonky on this image, just like with how they formatted it with the squares and everything. But let's start off with functional groups. So I'm just going to work my way from left to right. First up, we have an arene ring. Then over here we have a carbonyl. And remember, when we have a carbonyl, we can't just say carbonyl for our functional group. We have to look to the left and right and see what else is beside it. So on one side of it, we have a nitrogen. So this is an amide. Okay, then down here we have a carbon-carbon triple bond. That's our alkyne. Then here we have an oxygen with carbons on either side. So that is our ether. At the bottom, we have a nitrogen attached to some carbon. So this is just an amine. Then we have an alkene, a carbon-carbon double bond. And then we have a couple of carbonyls. So this carbonyl, on one side, we have an oxygen, making it an ester. Then for this carbonyl, we have carbons on either side. So when we have a carbon on either side, what we have is a ketone. We then have an OH, our alcohol. And finally over here, it's kind of weird because we have a box here. This box is for like hybridization things, but these are carbons that are part of the skeletal structure. So here we have an oxygen with carbons on either side. That is an ether. Now, if it's part of a 3-membered ring and it's an ether, like if it was like this, then that's a different functional group called an epoxide. But here for 4-membered rings, we don't have a different designation for it. In the answer key it says, just for funsies, 4-membered cyclic ethers are called oxetanes, O-X-E-T-A-N-E. But I've never heard of that until this moment. And so why would y'all know that? You wouldn't. So we would just call it an ether. So that is part 1 of this question of the functional groups. Any questions on these functional groups before we move on to hybridization? the most common mistakes are going to be with naming carbonyl compounds and just checking what's on either side. And then second most common mistakes after that are confusing ethers, alcohols, and acetals. I think that if you can get clear on those and seeing them in different contexts, then you should be solid on the functional groups. For the ketones, do we need to circle the C's? So this is a thing that, like, me as a grader, I'm like, no, if you call it a ketone, I know that you get it's a ketone. And so, but I remember there was some, like, TF discussion about this in the Slack that was essentially, like, circle everything that you would need to determine that it's this functional group. So I would say yes, circle the carbons on either side just to be safe. But I don't think it's that big of a deal. And honestly, if you lost points because you didn't circle the carbons and it was a ketone, I would do a regrade request and fight that. But that is just me. So maybe to be safe, circle it, but I don't think it's a big deal. Also, I'm like trying to like center myself in the video. I think I need to scooch this way because I have the little section recording. Okay, then let's look at all these boxes for hybridization. I'm going to do hybridization in purple. Now, hybridization, we are going to go based on our electron domains rule, where if we have 4 electron domains, then we are sp3. If we have 3, we are sp2. And if we have 2, we are sp. But then we have one exception to this glorious trend, and that exception is our neighbor rule. So neighbor rule has 3 parts. 1, it has to appear sp3. 2, it has to have a lone pair. And 3, it has to be adjacent to a pi bond or an empty p orbital. So with this in mind, let's start. I'll start up here. So this oxygen, well, this oxygen has 1 electron domain here, and then it has 2 lone pairs. So it has 3 electron domains. It's sp2 hybrid. Then we have this carbon here at the edge of the alkyne, and that has only 2 electron domains, so it's sp hybridized. Oh, and yes, it is recording. I record not in Zoom because Zoom does kind of crappy videos. Like, it just, like, compiles it together. I use a software called OBS to record, so it is recording. Then, up next, we have this nitrogen here. This nitrogen has 2 hydrogens, so that's 2 electron domains. It has this carbon, that's another electron domain, and it has a lone pair. So it's 4 electron domains. This is going to be sp3. Maybe, again, if we get an sp3, just pause and check. Is it adjacent to a pi bond or an empty p orbital? No, this is just another sp3 hybridized carbon. Okay, then we have the carbon over here on this alkene. It has 1, 2, 3 electron domains, so it's sp2. Then we have this oxygen. This oxygen has 1, 2 electron domains of bonds, and then 2 lone pairs, so 4 electron domains. And then we check, it appears to be sp3. It has a lone pair, and then is adjacent to a pi bond. Yes, indeed it is. So this is our one exception, our sp2 by our neighbor rule. And you don't need to write out neighbor rule or anything, but I think it's good for you to have it on your mind as something to check out for, because that's typically the only time that students miss things in hybridization. Then over here, we have this OH. It has 2 bonds, 2 lone pairs, 4 electron domains. It's sp3 hybridized, not next to any pi bonds. And then over here, we have this carbon, which is attached to 3 other carbons, and it has a little hydrogen that's hidden there. So 4 electron domains, so sp3 hybrid. Did I miss any of these, or are there any questions on these for the hybridization? I know I kind of just like plowed through it, but it's also kind of the thing that we're just kind of looking for mistakes at this point.
Colton, can you say that one more time, the neighbor rule?
Yeah.
Why the sp3 up on that ester is not, or it is an sp2 instead of a sp3?
Yeah,
please?
and I'll go back to the section 1 notes where I talked about this. So there's only one exception to this, like, number of electron domains and hybridization. Normally, this is the case for everything, except for when we have this special circumstance where we have an atom that appears to be sp3 hybridized, and we can maybe look at this nitrogen, for example. This nitrogen has 4 electron domains, 2 hydrogens, 1 bond to carbon, and a lone pair. So it appears to be sp3. It has a lone pair, and it is adjacent to a pi bond, meaning right next door we have a pi bond of these p orbitals. So when we have all 3 of these things coming together, this lone pair, it could be in an sp3 hybridized orbital, totally. But if it does that, essentially it is localized on that nitrogen. It can't spread out. If instead it were to put this lone pair in a p orbital, like a pure p orbital, have one pure p orbital and do a hybridization where the other ones are sp2, then what it's able to do is it's able to line up this p orbital with the p orbitals in the pi bond and delocalize via resonance. And so it spreads out that electron density, which is really stabilizing for a molecule. So delocalization of electrons, whenever you can do it, is going to be helpful. And so what we get is actually this thing, this nitrogen, while appearing to be sp3, is actually going to be sp2 in order to put its electrons in a lone pair, to put its lone pair electrons in a p orbital and do this delocalization. Did that make a little bit more sense talking through it, Gabrielle?
Yes, thank you so much.
Totally, yeah. Cool. And then I'll go back here. Any other hybridization questions? Okay. Well, then I will go on to part B here. We have ascorbic acid. Love her. Vitamin C, emergency. Fights off a disease called scurvy. We don't care about the background. We've labeled 3 protons here, A, B, and C, and they want us to match them to these different pKa values. Well, they all look like alcohols, right? And what's our kind of standard range for alcohols for pKa?
15 to 20.
Yeah, like different classes do different things. I think that ours, do we do 15 to 20 or do we do like 14 to 16? It might be 15 to 20. I just don't fully remember.
The handout says 16, but then it says can range 15 to 20.
Okay. Oh, pop it in with the footnotes, having all of it. Yes. So yeah. I typically think of alcohols like around 15, 16. So I would just say like around 16. Broad strokes. Again, it really depends. But this is the thing. We only have one pKa value that's even really close to that. This one. And the other 2 are much, much lower pKa, so much stronger acids. So something else must be going on. So if we look at these alcohols, which of these alcohols looks like it might be the most normal? Like it doesn't have any other factors going on? Or do you even know kind of like what to look for with that? Like what stands out to you about these 3 different alcohols?
I would say like B and C, they are connected to like a double bond.
Yeah.
While A is like just kind of by itself off of a regular sigma bond.
Excellent, excellent. And we could even try just looking hybridization-wise. Like, this one is sp3 hybridized, just like normal. It has 2 bonds, 2 lone pairs. This one is our neighbor rule. It appears to be sp3 hybridized, has a lone pair, and is adjacent to a pi bond. So both of these are sp2 hybridized, and there's going to be some resonance involved over here. So now, does resonance make things more acidic or less acidic? So, resonance is going to make things more acidic. If we look at our little face-off from section 2, the way that we can think about it is in terms of the conjugate bases here. So imagine we had an O- here where there is resonance versus where there isn't. When we have resonance, it helps us spread out that negative charge, and it stabilizes that conjugate base, making it a weak conjugate base. So the conjugate acid of it is a stronger acid. Strong acids have weak conjugate bases. Whereas this negative charge is just localized on one oxygen. It's not spread out. So if we have resonance available to us, the more resonance we have, the more acidic it is. Okay, so given that, we would expect B and C to be these two up here, the more acidic. And then our plain Jane alcohol A is probably going to be this one greater than 14 to be exactly what I expect, because this is no resonance. So now, to look at the resonance between B and C, let's try to draw out what those resonance structures look like. So I'm going to draw the conjugate base for each one of these. I'm going to just abbreviate this. I'm going to call this whole thing R. So this is the conjugate base of B. And then the conjugate base of C I'll draw as well. So the conjugate base of C would be if we deprotonated at C. So now, let's start off with B. With B, we can push electrons down and go from this lone pair. Remember, we want to start where we have a buildup of electrons, where we have a negative charge. But then if we make a bond here on this CO, turn it into a double bond, this carbon already has 4 bonds. So we have to break a bond. And if we're doing resonance arrows, can we break sigma bonds? No. Resonance is only going to change atoms or electrons in lone pairs and pi bonds. So then what we have to do is we have to push our electrons from our pi bond. And for right now, I'm just going to put it over to carbon, but we'll see that there are a few more things that we can do with that. So we have a resonance structure now where we have a double bond O. So that came from this arrow right here. This arrow turned into that double bond. And then we have a negative charge on a carbon. Negative charge on carbon, not great, right? But we can go on and do even more resonance. So we could push electrons from this lone pair, make a pi bond in between these two carbons, and then break this pi bond. So let's see. And I'll just again trace the arrows here with the electrons. This lone pair came from that arrow from the double bond, the carbon-carbon double bond in the first one. Okay. And then in this structure, we now have this arrow has turned into a double bond between these two carbons. And then this arrow has turned into an additional lone pair on the oxygen, giving it a negative charge. So we have 3 pretty stable resonance structures for this deprotonation of B. But now, if we look at C, we can try the same strategy here. We are going to push down, form a double bond, but then this lone pair, we have to break this pi bond, and we're pushing electrons this way. And so the only thing that we can really do is push the electrons onto this carbon. So if we do that, we now have a lone pair on this carbon, and we would have a double bond to the O up here. And so the electrons in this lone pair made the double bond, and then over here it formed the lone pair. But with that, we're not going to be able to spread out these electrons further. So here, if we pushed back in and we tried to get over to this, like, carbonyl, well, here we have to break a bond with this carbon that already has 4 bonds. And so the only thing we can do is go back to where we started over here. So given that, C has 2 acceptable resonance structures, whereas B has 3. B has more resonance. And moreover, B puts the negative on oxygen for one of its resonance structures, whereas C puts the negative only on carbon. So given that, we have that B is more stabilized by resonance, so B is most acidic. So that is going to put us over here with B up top, and then C is going to be the intermediate one. Questions about this and using kind of resonance structures for explanations? So, great question about, can y'all do the R abbreviation? That's a great question. Generally speaking, if it's not too much to draw it out. Sometimes we will tell you explicitly on exam, abbreviate this molecule with an R in this way. The other thing that you can do, if you want to be kind of bulletproof about it, is you can say, in this case, R is going to be where we cut this bond off. So it's all of this. So you can define what your R is up top to make it really explicit. For this first exam, I don't think that we're going to have anything that would be worthwhile to abbreviate that would actually save you much time. Okay, and then another question. Could you not arrow push down towards the H and R group on the left structure for C? Because you can't break a sigma bond to move electrons. Are you thinking, like, could we not do this and then move these electrons over here?
Yeah, sorry. I meant the right structure, but like down the left side of the the ring. Yeah.
So here, this is sp3 hybridized, no resonance. Remember, to do resonance to have electron delocalization, you have to have a pure p orbital, and that's sp3, so no resonance. That's a great question.
Colton, can I ask one question about number 1A really quick?
Totally.
So if there were to be any like positive or negative charges, those would be explicitly written in there. Is 100%. That correct?
100%.
Okay.
And
okay,
I
perfect.
doubt that we would give you something charged on like this type of question.
Okay. So
yeah.
all we need to do is just, consider lone pairs that need to be added, and that's
to make it neutral.
It.
Yeah, exactly.
Okay.
Mm-hmm.
Okay, thank you.
Yeah. Cool. Then I think I'm going to move on to number 2. So, classic question, especially for our class, the way we teach reactions, the way we teach organic chemistry. We are going to have 2 unknown molecules. We need to figure out how they are going to react with each other. And so that involves building full MO diagrams and kind of understanding all the homo-lumo intricacies. So, first thing to do, like just starting off with some checks. We want to calculate our number of valence electrons, and we want to calculate our number of atomic orbitals. And this is just a check for us so that we make fewer mistakes. So I'll start off, okay, let me draw out the full Lewis structure. There are 3 H's here. There are 2 lone pairs here. So this formula is C2, because we have a carbon here and a carbon here. Then we have 4 hydrogens and an O. H4O. So if I calculate my valence electrons, carbon has 4 valence electrons each, so 4 times 2 is 8. Then hydrogen, we have 4 of them, and they have 1. And then oxygen has 6. So if we add these together, 8 plus 4 plus 6, that is going to give us 18 valence electrons. Then, for the number of atomic orbitals, our rule is every hydrogen only contributes one atomic orbital, a single s orbital. So 4 of them, 4 hydrogens, each are just contributing one s orbital. And then, for all of our atoms that are not hydrogen, they're going to be contributing 4 atomic orbitals. They're going to be contributing one s and then 3 p orbitals. So we have 3 non-hydrogen atoms, 2 carbons, 1 oxygen, and each one's contributing 4 atomic orbitals. So we have 4 plus 12, that's going to be 16 atomic orbitals. And the reason that we are doing this is because our number of atomic orbitals is going to equal our number of molecular orbitals. So that's just going to be a little check for us when we start constructing and listing out all of our molecular orbitals. So now I'm going to partition off the top here just to do some brainstorming planning of writing out all of our molecular orbitals. So we've done this kind of prep work. And now I'm going to start off by listing our bonding molecular orbitals. So just every time I see a bond, I'm going to write down the molecular orbital. We have 3 sigma CHs. We have 1 sigma CC. And actually we have 3 sigma CHs and we have a 4th sigma CH. So we have 4 sigma CHs. Technically, one of these is like an sp2 carbon with a hydrogen. This is an sp3 carbon with a hydrogen. We don't care about the differences between that for our MO diagrams. That's a little bit too nitpicky here. We just care about the identity of the 2 atoms, not their hybridization for this level. Okay, then I have 1 sigma CO, and that's the single bond here, and then the double bond is going to be a pi CO. Okay, so now that we've listed all of our bonding molecular orbitals, we know for each bonding molecular orbital, we have an antibonding molecular orbital. So we have 4 sigma star CH. We have 1 sigma star CC. And we have 1 sigma star CO and 1 pi star CO. Okay, if I count this up, this is 4, 5, 6, 7. 7 and 7, 14, but we're supposed to have 16 molecular orbitals. Which ones are missing? The lone pairs. So the non-bonding on oxygen, we have 2 lone pairs. Cool. So we've listed out all 16 of our molecular orbitals. So now let's start constructing our energy diagram. So we'll create an energy axis over here. And we know our general categories for our energy is we have sigma, pi, non-bonding, pi star, sigma star. So starting off with our sigmas, we have 3 of them. Well, within sigma, we were told that the lowest is sigma CH, then we have sigma CC, then we have sigma CX. So we only have 1 of these for each. We don't have any within these categories. And so we can just start building from the bottom. So we have 4 sigma CHs. Then we have our sigma CC. And then we have our sigma CO. So that's all of our sigma. Then we have our pi CO, our only thing in the pi camp. We have 2 lone pairs on oxygen, the only thing on our non-bonding camp. Then we have our pi star CO. And then for a sigma star, we know it's going to be exactly flipped what we had at the bottom. So we know that the sigma CH is the lowest. So the sigma star CH is going to be the highest. Then we have after that the sigma star CC and the sigma star CO. So it's going to be exactly mirrored here. Okay, so we've listed out all of our MOs in energy order. So now we are going to use our valence electrons that we count up here and just populate from low to high energy. So 18 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So our highest occupied molecular orbital is going to be our lone pair on oxygen. And then our lowest unoccupied molecular orbital is going to be our pi star CO. Generally speaking, if you are like putting electrons in antibonds for your MO diagram, you have done something wrong. Also, generally speaking, if you do not have enough electrons for your bonding orbitals, you have done something wrong. For non-bonding, depending on if you have like a carbocation or lone pairs, it'll depend on if they are like occupied or not, but that should be the general guide. Somehow I'm missing the sigma CO. Can you show where that is in Lewis structure? Yeah. So here we have a double bond between carbon and oxygen, and a double bond is made up of a sigma bond and a pi bond. So those are our two bonds here. Oh, there we go. Cool. So we have done this for molecule A. Now let's do the same thing for molecule B. So I'm going to list out the full Lewis structure. I'm going to draw in any hydrogens that were implied. And this one's tricky. We have a lone pair on here because we have a negative charge. And normally this carbon, if it was neutral, would have 3 hydrogens. But now, if we have a lone pair, we're only going to have 2 hydrogens because carbon with a negative charge has 3 bonds and a lone pair. Okay, so our molecular formula, we have 1, 2, 3, 4 carbons. Then we have 1, 2, 3, 4, 5, 6, 7 hydrogens. Now, for our valence electrons, well, each carbon contributes 4, so 4 carbons, each contributing 4 valence electrons. Then all 7 hydrogens contribute 1. And then we have a negative formal charge, so we're going to add 1 more electron on. So overall, we have 16 plus 7 plus 1, so 16 plus 8, which is 24 valence electrons. Then we do our number of atomic orbitals. Well, again, we know our 7 hydrogens each contribute 1 molecular orbital, or 1 atomic orbital, the s orbital. And then our 4 carbons each contribute 4 atomic orbitals, the s and 3 p's. So that's 16 plus 7, so we should have 23 atomic orbitals, which means we have 23 molecular orbitals. So now I'm going to do the process again of listing out my bonds. So sigma CH, I'm seeing 1, 2, 3, 4, 5, 6, 7 sigma CHs. Then sigma CCs, I'm seeing 1, 2, 3. Then we have a pi bond, so we have 1 pi CC. And I think that's all the bonds I see. So then we have our antibonds. So we have 7 sigma star CH, we have 3 sigma star CC, and we have 1 pi star CC. Okay. Then that's going to be 11 and 11, so that's 22. We're missing 1 molecular orbital. What is it that we're missing? The lone pair. So we have a lone pair on carbon, N sub C. And then I think that this is the thing, like in the classes before, when there's a carbocation, my classes in the past have done 2PC, but I think Serenia prefers the notation NC plus for a carbocation, and then here NC minus for a lone pair. So again, I think the plus or minus will be kind of like obvious based on the context, but like if you put the plus or minus, I think that that's like an indicator for whoever's reading it or grading it, that you know what's going on, and also it's kind of giving more hints to your grader to be like, they understand it. Okay. So now we do our energy ranking just like before. So lowest were the sigma CHs, 1, 2, 3, 4, 5, 6, 7. Then we had the 3 sigma CCs. Then we had our 1 pi CC, we have our lone pair on carbon, then our pi star CC, and then we just do the mirror, so sigma star CC, and 1, 2, 3, 4, 5, 6, 7 sigma star CHs. Then we populate with, we had 24 valence electrons, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So our HOMO is going to be that lone pair on carbon, and our LUMO is going to be the pi star CC. So we have built our MO diagrams, we've identified the HOMO and LUMO. Any questions on this process that we did? Okay. So now, the follow-up for these types of questions is, given that we've done the full MO diagrams and we know the HOMOs and LUMOs, we can then start to predict how these molecules are going to react. So, here, let's look at it. We have lone pairs on carbon and oxygen. And lone pairs, if we think about our short list of good donors, lone pairs are our best donors that we can have. And specifically, if we had to think about which one's better, well, we know electronegativity makes things lower in energy, right? So technically, our best donor is over here. And it's because carbon is less electronegative than oxygen. And so this is going to be a slightly better donor. But honestly, this is a great donor, so I would not count it out. Maybe I'll do kind of green and then like a muted green for second place. But then for acceptors, we have the pi star CO versus the pi star CC. Now, in our acceptor shortlist, we said the best thing was an empty orbital, but empty orbitals are hard to come by, especially in this economy. So our next best was a pi star, with the exception of pi star CC. So pi star CCs are not great acceptors, but all other pi stars are pretty good acceptors. So, given that, we are going to come here and we're going to say our best acceptor is the pi star CO over here. And then the kind of loser acceptor, I'll put over here in pink. So now we have to think, okay, is B going to be our donor and donate like this into the accepting orbital of A? Or is A going to be our donor and donate into the accepting orbital of B? And here, we're going to have the best interaction between this molecule B being the donor and molecule A being the acceptor. And it's because A is the only one that has a really good acceptor. So, our donor is going to be the lone pair on carbon over here, and I'll draw in that lone pair explicitly. And our acceptor is going to be the pi star CO. The way the boxes are placed, it makes it seem like, oh, okay, this is the acceptor molecule, this is the donor molecule. No, it's asking us how are these going to interact, and then what's the donor and acceptor. So don't let the layout fool you. And then when we do that donation, our lone pair, we're going to do a curved arrow into the pi star CO, and we are going to attack the carbon side of it. And remember, this is because when we have polar bonds, then in the bonding molecular orbital, we have larger lobes. Oh, that was horrible. Blah. We have larger lobes on the more electronegative atom, kind of the negative lobe and the positive lobe here. But then in our antibonding orbital, we are going to have larger lobes on the less electronegative atom. So we're going to be attacking carbon because that has larger acceptor orbitals. It also has a partial positive on it. But now, if you remember nothing else from this MO section today, the thing I want you to remember is when you put electrons into an antibond, the bond breaks. And again, I normally, like when we're in a synchronous classroom, we are doing chants. We are like full on like Pavlovian conditioning. Electrons in, antibonds, make the bond break. But we're in Zoom and I am talking to a little camera and a microphone. So we have put electrons into this pi star antibond, so we break the pi bond. And we're going to push the electrons from that bond up to the oxygen. So now when we draw the product of this, well, anything that didn't really involve these two, or our arrows, we keep exactly the same. So I'm going to start drawing with this. So that's all exactly the same. But then this carbon over here, which I'm going to label with like a yellow dot, that just made a bond with the orange dot. So that's going to be our orange dot, that's our yellow dot. And then our orange dot had some other things attached to it. Well, it had a hydrogen and it had a methyl. And then it also still is going to have a single bond to an oxygen. We broke the double bond. And now it's going to have a negative charge on it. And it's because this arrow took the electrons in that pi bond and made a third lone pair on the oxygen to make it a negative charge. And with that, we are done with question 2. Any thoughts or questions on this before we move on? Oh, actually, I'm so sorry. We are not done with question 2. There are 2 more parts. So, why don't I finish that real quick? So now it's talking about, okay, well, the second step of this synthesis, we take the product from the first one. So I'm just going to redraw that product here. And what I'm going to do is, remember, we can imply this hydrogen because it's a skeletal structure. So we have 1, 2, 3, 4, 5, 6 carbons. Lone pair on one side. 1, 2, 3, 4, 5, 6. And then we can have our O like this. Okay. So now it says that this is going to do an acid-base reaction with acetic acid. So, pop quiz. Do you think acetic acid is an acid or a base? I don't mean to be super snarky, but just a little bit snarky. It's going to be our acid, so that means that this other thing is going to be the base. So, what is the thing that looks like it's going to be the electron donor and is going to grab the hydrogen that's on this second molecule? Well, the donor is going to be the lone pair on oxygen, right? Like, that's where we have a buildup of negative charge. And then the acceptor is going to be whatever the accepting orbital is here for us to give up a hydrogen. So if I'm going to actually draw this out here, so this is an OH bond, and if we are trying to take this hydrogen, we have broken the OH sigma bond. So the accepting orbital is sigma star OH. So with this in mind, we draw our arrows. The lone pair on oxygen is going to go and grab the hydrogen by attacking the sigma star OH. That breaks the bond. So our products that we get out of it, from acetic acid, we now have acetate, so the negative charge on the oxygen. And then we have this oxygen has grabbed a hydrogen. So that is our product. The last question on this says, instead of acetic acid, what if we used trifluoroacetic acid, which is just kind of an analog of acetic acid where we've added 3 fluorines here instead of 3 hydrogens? Okay, would we expect this to occur faster or slower? So really what we're asking about is TFA a stronger acid or a weaker acid? Well, we know that if we have halogens on a molecule, this is going to cause induction to occur. Induction is when these negatively charged halogens, electronegative halogens, pull electron density towards it. And what that does is it stabilizes the conjugate base here, the negative charge, because you have little things tugging at those electrons, spreading them out a little bit. And so we have our acidity rule of more induction equals stronger acid. So stronger acids react faster than a weaker acid reacts slower. So now for real, we are done with question 2. Any questions or comments on this? I know someone said acid-base things were a little rough. So, will you ever need to do this with wedges and dashes? Eventually. For exam 1, no.
Could you explain one thing real quick? Why does induction lead to a faster rate in part D again? Is it because we have more acid that can be attacked?
Not exactly. Let me bring up from section 2. So, if we think about a version where we don't have induction versus a version where we do have induction, both cases we have a negative charge. Having a negative charge on a molecule is not super stable. And so, in order to have a weak conjugate base or a stable conjugate base, we need to think, how do we spread out that negative charge? When you have induction, these are creating a little bit of a dipole where they are literally pulling the electron density a little bit away from the oxygen and towards the fluorines that are super electronegative. Now, when it does that, the electron density for the negative charge goes from being really localized around this oxygen to now being like tugged a little bit. And it's spreading it out over a slightly larger area. And so when we can spread out that negative charge, we are actually stabilizing the molecule. Because remember, it's not stable to have a bunch of negative charge build up in one area. That's why something like resonance, where we fully delocalize a charge, is so stabilizing, because you are really getting to spread out that negative charge. It's not isolated on one atom. Induction is like a really weak form of that spreading out of electrons that we see in resonance. I typically say, like, induction is like saying kind of there, it'll be okay. And resonance is like, I'm your ride or die. I'm going to take this on with you. We'll get through this together. So resonance definitely way more stabilizing, but induction still does a little bit to spread out that negative charge, making this a more stable base, meaning its conjugate acid is a stronger acid. Did that make more sense? Work. Why is the acceptor sigma star OH? Why is it not pi star CO? So great question. And here, you totally could have a version where this attacks the pi star CO. Sorry, my dog is, I don't know if you can hear her through the camera. She is a little rowdy right now. So this is totally something that you could imagine would happen. Why doesn't that happen? Well, part of it is just kind of perfunctory. They've told you it's acid-base. So if they're telling you it's acid-base, then do an acid-base reaction. Don't attack the pi star. The other part is acid-base reactions are just generally way faster than like a nucleophile-electrophile attack. So if you have the option of doing an acid-base reaction, those typically happen really rapidly and they happen first. So that's the big reason. Great question. Cool. I'm going to move on to 3. Chair. We love a chair. Yeah, I got a little like hexagon necklace this summer, like a little chain with a little hexagon on it, and wore it for the stereochemistry lecture and for exam 1. So there you are definitely going to have a chair question on the exam. And the classic way of asking about chairs is we'll ask you to draw 2 chair structures, one that's more stable, one that's less stable, and they're like ring flips of each other. And during section 3, I like walked through how to do that kind of beat by beat at the end of the section video. So I'm going to do that here for this. Other things to kind of keep in mind is if you are just asked to draw the most stable, then generally speaking, find whatever your largest group is. In this case, it's the tert-butyl. And you want to make sure you put that tert-butyl equatorial. Now, there are some cases where there special things will happen where we don't have to put it equatorial. But for the most part, we put our biggest thing equatorial, and then we take it from there. So what I'm going to do, I'm just going to draw a standard chair. And then I'm just going to assign this carbon to one of the carbons in the chair. But we have to be careful because this being on a wedge means that it's going to be in an up position on the chair. And so some of our positions on the chair, like this position is an up axial. And remember, up is compared like looking at it as an eyeball from above. So that, if we assign it there, that's going to be up axial. We don't want our like tort-butyl to be axial, but it has to be up. What if we instead put it here? Well, the positions on this carbon, the up position is equatorial. So that would put our tort-butyl up and equatorial, so we are going to do that for our most stable one. And I also think it's really, really good form to, if you put one substituent on there, draw the other bond and put the H on it, just to make it really explicit for the grader of like, okay, this is up an axial, or sorry, this is up equatorial, this is down axial. Also be trying to make these like literally like copy and paste from the textbook of what you see for all of these. And by the textbook, I do mean the class notes. But the bond angles just need to be really specific. I was grading the chair question on the homework, and it was a little rough. A lot of people did really well, but some of them were a little rough. So now, once we have assigned our first position, then we need to think about going clockwise around. So then we did skip one, and then we had this dot. So if I'm looking at this from above, clockwise is going to continue around this direction. So I'm going to skip one, and then my dot is over here. Okay, now this one we have a methoxy, and it needs to be on a dash, which is down. Well, our two positions for this position on the ring, our two substituents, I guess, the angles, we have down axial, so that's where our OME is going to go, and then up is equatorial for a hydrogen. Then if we continue clockwise, we have an oxygen, so I'm just going to replace this carbon with an oxygen. Okay, then if we continue even more clockwise, we have this position, which we have it on a wedge, so it needs to be up. So here, our two positions are, we have an axial down, and we have an equatorial up. Now the way I've drawn this, these two I put directly under each other, which makes it kind of hard to see. Technically, this should be more kind of over here, and so they won't bleed together as much. But I'm going to put that ethyl on the up position, the up equatorial, and then on the down position, we just have an axial, which I'm going to do like this. So, we have drawn our most stable chair conformer. And with this, we see that we have two things equatorial, the ethyl and the tort-butyl, and we still have to have one thing axial based on how we've done this position in the ring. But again, we have our two largest things equatorial, and that's going to be more stable. The other thing that I saw people do to make mistakes on this was when they were assigning it, instead of doing this clockwise, they went the opposite direction. And if you do that, you're actually going to make the enantiomer. And so it's just not going to be the right molecule. But that's all for question 3. Any questions on this? Yeah, this is a pretty short chair question. The other thing I would watch out for with chairs is I would watch out for like bicyclic structures. I'd also remember kind of things with Brett's rule. Like that kind of stuff was also in chair land, so just don't forget it. Last question here, question 4 for the mini exam. Pseudophenamine? Sudafed. Oh my gosh, pseudophenamine. I think that's what this is. This is like what you have to like give your ID at the pharmacy to get. I think it can be used to make like meth or something. But we are asked to circle all stereocenters. The shortcut for finding stereocenters is look for things that have dashes and wedges. This and this. But I'm going to show you my favorite trap for that. My favorite trap is something like this. Students will often look at this and circle, oh, that's a stereocenter, there's a wedge. But remember, the technical definition of a stereocenter has to be attached to 4 different things, and these are 2 methyls, so it's not a stereocenter. So just watch out for that. Second thing it says is, after we have circled the stereocenters, we want to assign R and S. So, I will start in on that. Well, first priority is definitely going to be our OH, and then if our OH is on a dash, then our hydrogen is going to be on a wedge, so that's our 4 position. And then we are comparing carbon versus carbon. Both of these carbons are carbon, so we have to look at substituents. Over here, carbon, carbon, carbon. Over here, carbon, hydrogen, and nitrogen. Who wins? Well, the nitrogen does, because it is the higher atomic number of our substituents. So we have 2 over here and 3 over here. Is the N technically a stereocenter as well? Well, the N is only attached to 3 things. It has a lone pair, but a lone pair is not a 4th thing it's attached to. When we think about stereochemistry, we are thinking about like actual bonds. You could have a nitrogen stereocenter, and a nitrogen stereocenter would look something like this. So it forces the nitrogen to have a positive charge, and it has to be connected to 4 different things on the nitrogen. So you could have that. I've never seen Harvard ask about a nitrogen stereocenter, but like I tutor some students at the University of Georgia for organic chemistry, and they ask about nitrogen stereocenters. They are very mean about it. In some way, like Harvard's organic chemistry is way easier than other schools because other schools require a lot of technical detail. In other ways, ours is a lot harder because we make you have to understand reactivity a lot more. So win some, lose some. Okay, so now I look at these and I ask myself, what mode am I in? Well, 4 is coming out of the page at us, so we are in opposite day mode. Okay, so I trace my 1 to 2 to 3. It's clockwise, but it's opposite day because 4 is coming out of the page. Clockwise is normally R, but opposite day means this is going to be an S stereocenter. Then I'm going to do the same process over here for the other one. Well, the nitrogen is definitely 1. The hydrogen, which is going to be a wedge, is 4. Then we're comparing carbon versus carbon. Well, this carbon has an oxygen attached to it. This carbon only has carbons attached to it. So this one over here wins is priority 2 and priority 3. We trace 1 to 2 to 3. It's clockwise, but our 4th priority group is coming out of the page at us, so it's opposite day. So clockwise would normally be R, but opposite day, it's going to be S as well. So that is this stereocenter. They are both S. Okay, so now one thing I'm going to do is I'm just going to like take a screenshot of that. So she's preserved. She'll be around. But it's going to make the next part hard if we have all this annotation on it. And so I want to have a clean version as well. So, boop, boop, boop. Okay. So we've circled our stereocenters, labeled them. They're both S. Now, they've given us these other molecules and asked us to figure out the relationship of these to the original. Well, here we see that this stereocenter is exactly the same. The OH is on a dash. But then this one is on a wedge, whereas originally it was a dash. So all of our stereocenters are on the exact same position here, and one of them was the same, and one of them swapped. So if some but not all swap, that is our junk drawer. That's diastereomers. And I'll circle that. Then, if we look at the next one, here both of them swapped. They were both on dashes originally, now they're both on wedges. And so if we are all swap, that is the enantiomer. And I'm going to do my little jingle of enantiomers from last time, which I know is a little bit annoying, but I want it in your head when you were taking the exam. And it are 2 different definitions of enantiomers. One of them is stereoisomers that are non-superimposable mirror images. So you make a mirror image and you can't put it back on top of itself. The other one is if you put all of the like stereocenters together, all the stereocenters swap from R to S or S to R. And we can think about like two ways of drawing it. We could either specifically draw the enantiomer by drawing the mirror image, or we could keep the stereocenters exactly where they are and swap the wedges and dashes. And so my little chant for it is 1, 2, ready, go. Enantiomers, clap, clap, non-superimposable mirror image. Enantiomers, clap, 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 all swap. So all swap enantiomers, some but not all swap diastereomers. Okay. Then we have another one down here. This one down here, we have the OH is swapped, but the NH2 is the same. And so we know that this is going to be some not all swapped, so this is another diastereomer. And then they're asking us a couple of conceptual questions. So the key thing that you need to know here is enantiomers have the same physical properties. Diastereomers, not necessarily. So, is it true that this form will not necessarily have the same melting point as the one at the top of the page? Well, they're diastereomers, so yeah, it is true that these are not going to necessarily have the same melting point. Now, these will necessarily have the same solubility. Solubility, just like melting point, physical property. No, it's not necessarily true. So this is false. Because these are diastereomers, they don't have to have the same physical properties. So that's question 4. Any questions on this one? Enantiomers. Non-superimposable mirror image. Enantiomers. All swap. One of my UGA Oakham students, they have their second exam this Wednesday, and it's over stereochemistry things. They had a whole other first exam before it, but yes, I've been spreading the gospel of the enantiomers song. Cool. Well, if y'all are open to it, with the last I'm gonna do 10-ish minutes just because I started 5 minutes late. I'd like to go through this question from Practical Exam 1B, just because I think that this is another good, classic problem for these first exams for Harvard's OCHEM, where we want you to be putting this, MO theory stuff into practice. We have the diagrams, but we also want you to be able to, draw arrows given structures and figure out what the MO, interactions are between things. So, this is from Practical Exam 1B. Let's look at it. It's wanting us to predict how these are going to react, and they do a long, multi-step reaction, kind of similar to what you saw in Lecture 4, things that are not on Exam 1. So you would not be expected to, just figure out the products of this, but what they've done is they've given you structures for each of these sub-steps, and they want you to figure out what happened, to figure out the donor and acceptor, and to draw the arrows. So, we start off by playing a little spot the difference game. What is different? Well, this molecule and the product has a hydrogen. This one's lost a hydrogen. So we know we need to get the hydrogen onto this oxygen. And now, the other thing I'm thinking about is what bond did we break? We broke the sigma HCl. So if we broke a bond, we put electrons in the antibond. So our acceptor has to be a sigma star HCl. Okay, well then our other molecule has to be the donor, and the donor has to be on oxygen. Well, what does oxygen have that's a good donor? It has a lone pair. So our reaction is going to be a lone pair on oxygen is going to go and attack the sigma star HCl, breaking that bond. That's step 1. Okay, step 2. What we have is, we don't care about the Cl girl anymore. We care about this protonated carbonyl. And we have this benzene ring with a alkene on the side. And here, I kind of see this has got to be this in the product. And then we know that these two have got to be this. So somehow we've joined this carbon with, well, we need a carbon that's connected to an OH. Well, that's an OH. So it's connected to this carbon. So let me do that. This carbon has got to be right there. Okay. Well, what bond did I break? Well, here, there's a double bond. Now there's only a single bond. So what bond did I break? Well, I broke the pi bond. So my acceptor has to be the pi star. In this case, it's going to be a CO. Okay. Then, what do I have that's a good donor over here? Well, we don't have a lone pair, but we do have a pi bond, a pi CC. And pi CCs are great donors. So what we're going to do is our pi CC is going to go and attack our pi star CO, which breaks that pi bond, pushing up. Okay. The next step here, it looks like this boy right here, just like plonk, attached over here to the carbocation. And if we have a carbocation, that's our best acceptor, right? So this is a NC plus, or like 2pC orbital. And our donor, well, it was the oxygen, so it's got to be the lone pair on the oxygen. So lone pair on the oxygen is going to go and attack the 2pC. And we only need one arrow for this since we didn't break any bonds. Now, this is where it gets harder. So now what they've done is they've given you the arrows, and we need to figure out what the donor acceptor are, and we need to figure out what the product is. Ooh, okay. Well, where did my arrows start? Well, the arrows started at a lone pair on oxygen. Okay, so that must have been my donor. And then where did we attack? Well, we attacked this carbon, and we broke the pi bond. So our acceptor must be the pi star CO. So now, when drawing the product, this benzene ring didn't do anything. So I'm just going to draw her because she is boring and she is just here. Then, when I'm doing an intramolecular attack, remember one of the strategies that we said is really helpful is to number things. So we have this carbon, or this oxygen, that can be our 1. It's now going to be connected to this carbon, 2, 3, 4, 5, 6. So we are going to form a 6-membered ring. So first thing I'm going to do is I'm going to draw a 6-membered ring. And this is my carbon 4. Like the one that was here connected to the benzene ring, that's 4. So I'm going to continue around like 5, 6, 1, 2, 3. And then I know some of these have to be oxygen, right? So like 1 over here was oxygen. So I'm going to erase the carbon there in the corner. I'm going to put an oxygen. And even more than that, it was an OH, because we didn't do anything that would have gotten rid of that hydrogen. So we still have an OH there, which means that this oxygen has 3 bonds. It has a positive formal charge. Now, carbon 2 up top, connected to 2 hydrogens. Okay. And then to carbon, or to position 3 here, which that's going to be another oxygen. So we could draw in these hydrogens if we want to, but we don't have to. We can imply them. And then the pi bond over here made a second lone pair on the oxygen. So this is just a neutral oxygen now. So I think we're good with that one. Like, I think we have done the product. Cool. Last one here for this step. Step 5, redraw the product that we did before. So, we have to get this product correct. And then we have a chlorine involved. And then they tell us the donor-acceptor interactions. The lone pair on the chlorine, so go ahead and draw on that lone pair, is going to attack the sigma star OH. So we need to break the OH sigma bond. So if we are doing something with sigma bond, and do you see how, like, the way it's written right now, OH, we don't have the bond drawn? So if we are doing something in our reaction that involves that bond making or breaking, we actually need to redraw that out explicitly, like this. So lone pair is going to attack the sigma star OH, which breaks the sigma bond. And so our products from this are going to be we have our benzene ring. And we have our 6-membered ring over here with 2 oxygens in it. And then we have HCl, hydrochloric acid. The very, very last thing, which I didn't look at, is just the structure of one of the intermediates is reproduced below. Draw the cartoon orbital representations of the molecules HOMO and the molecules LUMO. Well, this was for this step right here. And here, the HOMO and LUMO attacked itself. The HOMO was the lone pair in the oxygen. The LUMO was the pi star Cl. So let's draw those. So here we want NO, and here we want pi star CO. So, lone pair in oxygen, well, what's the hybridization of this oxygen? This is sp3. It has 2 bonds, 2 lone pairs, 4 electron domains. So I'm going to draw a big lobe and a small nub, and they need to be opposite phase. So that's a cartoon drawing, and I can put my lone pair in it if I want, or you could just leave it like this. And then the pi star CO. So we're going to have carbon and oxygen, and remember we have larger lobes on the carbon because it's less electronegative. So we're going to have big lobe, small lobe, small lobe. And I can just draw it like that. And that's it. So I hope that was helpful going through some of these questions together from the mini exam, the practice exam here. I am going to take a little break for like 5 or 10 minutes, and then I have office hours from 7:30 all the way to 9:30. So I have 2 hours of office hours. So feel free to come by and ask questions. Are there any questions on this before we break?
Can I ask a quick question about the shading for the pi star CO interatomic orbital?
Mm-hmm.
And why are the orbitals on the oxygen shaded?
Sorry, I meant to only shade one of them. So
no worries.
Basically, like if we had our normal, like let's say we had a CC pi bond, in the pi bond, the shading on the top and the bottom have to match. And so in the antibonding orbital, it's like the shading got mismatched. So one of the top ones is shaded and one of the bottom ones is shaded. Is that answering your question or no?
Yeah, that makes sense. Thank you.
Cool. Yeah. Other questions? Wow, the first section I'm finishing before my office hours start. Crazy. Wild. Cool. Well, thank y'all for coming. I appreciate it. And thank y'all for asking good questions. I know all the people watching the video appreciate y'all being here and like asking questions that they also probably have. So thank you. Goodbye.